Greetings. Welcome to the fourth lecture of Electronic Circuits 1. I am Razavi, and today we will continue to look at the PN junction. Last time we started developing the PN junction to see what it looks like, and then we would like to see its properties. So I would like to take a quick look at what we covered last time before we start the lecture today. So here's a quick summary. So in the last lecture we saw that there are two current conduction mechanisms, namely drift, which is given by the electric field that we establish in the environment, and parameters such as mobility and the concentration of electrons or holes. This is something that we obtain when we apply a voltage to a device. On the other hand, in the absence of a voltage, we could still have a current if we have difference in concentration as a function of distance. So, for example, if we have a certain gradient for the electron density or a certain gradient for the hole density, we obtain a diffusion current. And in a general device, both or one of these can exist. In the next step, we decided to take one piece of N-type silicon and one piece of P-type silicon and attach them together in a clean and regular crystal form. And we saw that upon doing this, some interesting things happen. We know that the N side has an abundance of free electrons, whose density we denoted by N sub N, and very few holes, whose density we denoted by P sub N for the N side. And the other side, the P side, has a lot of holes, P sub P, and very few electrons, N sub P. And we said, okay, if we attach these together, the device cannot exist as we started, because we have a huge difference between the concentration of electrons on the left and on the right, and also between the concentration of holes on the right and on the left. So diffusion will occur, and some electrons will roll down to the other side, and some holes will roll down to this side. So we have a diffusion current and a hole current. And these two create a net current between this side and this side. But that's strange because in equilibrium, this device is not connected to the rest of the world, which means we cannot have any net current in these wires. So what happens? Well, even if there is a current at the beginning, eventually it has to stop. And in a sense, it's a transient effect. So what stops this flow of currents? And we decided that, well, every time we take an electron out of the N side and move it to the P side, we leave behind positive charge in the form of a positive ion. So that is a positive ion. And every time we take a hole out of the right side and move it to the left side, we leave behind a negative ion. And it is these positive ions and negative ions that create a space charge here. And associated with this charge, we developed an electric field. We know that if we have net charge, we also have net electric field. That's Gauss's law, if you remember from physics. Okay, so an electric field is formed in this area. This area, this region, has no mobile charge carriers because all of the mobile carriers left. The electrons in this region went to the right. The holes in this region went to the left. So it's called a depletion region because it is depleted of free charge carriers. All right, so today we will continue to look at this in equilibrium. Our objective is to quantify the behavior of the device in equilibrium. For example, at what point does this current flow stop? Meaning that how much electric field do we have to develop here, or what voltage do we have to develop here inside for the currents due to these diffusions to stop? We would like to quantify that. And then, after understanding the equilibrium, we can go to other cases that are actually more interesting for the PN junction, namely reverse bias and forward bias. Very well. Now, before we jump into these studies, I thought today we look at one application of electronics to motivate us to learn some of these devices better, because as we will see, for example, a reverse biased PN junction can be beneficial in some applications, for example, in oscillators. So we will talk about an application right now, and then we will continue to look at the PN junction in equilibrium. In our Frontiers Electronics series today, we will look at Bluetooth as another interesting example of how electronics has found its way to our daily lives. Bluetooth is a wireless technology for transmitting and receiving data and other quantities, maybe even voice or video. As you can imagine, many of our little devices today are connected by Bluetooth. For example, you could have a printer connected to a PC through a wireless Bluetooth connection so that we can communicate data between them when we are printing a document. So we would like to see how Bluetooth operates. Now you remember we talked about the cell phone operation in the first lecture at a high level. So some of those ideas are still applicable to Bluetooth, but there are also some interesting differences that we will look at. All right, so let's begin by, again, building a transmitter for Bluetooth. So here's the situation. We have a, let's say, a laptop. Now I'll try to draw the laptop a little better than this. So let's say we have a laptop, and the laptop wants to transmit data to the printer. So here's our laptop, and we have a printer, let's say, over here. So here's a printer. I don't know how to draw a printer. There's a little sheet here, and that's the printer with a little tray, and we would like to transmit data. Okay, well, for wireless communication we need an antenna. So this guy would have an antenna on it inside. So that's the symbol for an antenna here. And then this guy would also need an antenna somewhere to receive the signal. Okay, so the laptop transmits this information wirelessly, and the printer receives this information wirelessly. Okay, so let's say that we have some data coming out of the laptop in the form of ones and zeros. Very simple, right? So we have a bunch of ones and zeros coming in, and this is the data that I would like to transmit. And I have an antenna here for the transmitter, and I'm hoping that these waves will come out and go to the printer. Now, if you recall, in the cell phone description in lecture 1, we talked about the fact that the antenna becomes a good antenna or a good radiator of electromagnetic energy only if the signal that is arriving here has a wavelength comparable to the dimensions of this antenna. So if the antenna is about this size, then the wavelength of the signal has to be on the order of 5 centimeters, 10 centimeters, maybe 20 centimeters, something that's range. But if the wavelength that's arriving here is much greater than the size of the antenna, then the antenna doesn't really radiate. It will actually operate like an inductor or some other component, but it doesn't operate as an antenna. All right, so here's the situation. We have this data rate coming out of the printer, and this is not very high frequency. In fact, in Bluetooth, the data rate is 1 megabit per second. So as a function of time, this has a rate of 1 megabit per second in Bluetooth. So the frequencies involved with this data are not high enough to allow us to build a small antenna. In other words, if you were to associate the wavelength to this information, the wavelength would be very large and would not allow us to build an antenna with reasonable dimensions. All right, so somehow we have to go from this data, which has only relatively low frequency components in it, to some high frequency that is friendly to this antenna. In Bluetooth, the frequency that goes here is about 2.4 gigahertz. So it's a very high frequency. That's good because the antenna doesn't have to be very large. In fact, in typical Bluetooth devices, you may not even see the antenna. It's a small component inside the device. All right, so how do we go from this data at 1 megabit per second to this frequency of 2.4 gigahertz? Well, here's a nice way. We will take an oscillator. So here's an oscillator. An oscillator generates a periodic output. So if I were to sit here, I would just see maybe a sinusoid. Okay? So it would just go up and down periodically. But what I do is, this oscillator has a control voltage. So here's a control voltage. We call it V control. And in fact, this would be called a voltage controlled oscillator, VCO. So I'll write here voltage controlled oscillator, such that when the data goes up and down between 1 and 0, this frequency goes up and down. So this frequency is still around 2.4 gigahertz, but its value is modulated by these ones and zeros. So if I go ahead and look at this waveform here, what I see is as follows. I have, as a function of time, a frequency of around 2.4 gigahertz, but it keeps jumping up and down according to these ones and zeros. So we have high frequency, then we have low frequency, then we have high frequency, then we have low frequency, etc. And the deviation here between low and high is not much, maybe a few megahertz or even less, but the point is that the frequency is modulated according to this data. In other words, this waveform now carries this information in it in the form of frequency modulation, which we call FM. So this is an example of FM, and for example, in your car radio, you also have FM. Okay, so at this point, we have a signal that has a high enough frequency. That's great for the antenna. And it is carrying all this information in terms of high frequency, low frequency, high frequency, low frequency. So that's great. And we are ready to go to the antenna. Typically, though, we would like to transmit a relatively moderate power so that we have a reasonable range between, for example, the laptop and the printer. Right? You may have 10 meters, 20 meters, or something. So what we do is place an amplifier between the oscillator and the antenna, so that the antenna is driven by a higher power. So we place an amplifier. You might call this a power amplifier that drives the antenna. So what is applied to the antenna is the same shape as this, except that it has a larger swing so that the antenna transmits a greater power outward. So this is a very simple transmitter that we could have for FM communication, or with some modifications for Bluetooth communication. And you can see that it requires amplification, oscillation, and many other functions that we are not showing here. Okay, so now that we saw that we have a Bluetooth system consisting of an oscillator and perhaps a power amplifier and antenna as a transmitter, we will jump back to studying the PN junction in equilibrium. So let me draw the junction again. So PN junction in equilibrium. So we have the junction in this form. Let's say N on the left side and P on the right side. And we have densities, as I showed you before, for electrons and holes. And now we have left these two terminals open. Nothing is connected from the outside world, and the device is in equilibrium. So as a result of a departure of electrons from the left and the holes from the right, we developed a depletion region here. So there's a depletion region in this vicinity consisting of positive ions on the left and negative ions on the right. Okay, so that's good. Now we would like to find the properties of this device in the form of some equation that tells us when this current flow stops. Now I would like to remind you that the density of electrons on this side is n sub n, holes p sub n, and on this side p sub p for majority carriers and n sub p for minority carriers. Okay, I would also like to remind you that let me change my color here, that when the densities are high enough, we can say that the density of electrons on this side is approximately equal to the density of donor atoms. So this is approximately equal to ND. And because we have a heavy doping of donors, the holes go down in density to a value given by Ni squared over Nd. And a similar effect occurs on the other side. So P sub P is approximately equal to the density of acceptor atoms, such as boron atoms. And then this drops to Ni squared over Na. Okay. All right, so we are looking for a condition at which the flow of electrons from left to right and holes from right to left has stopped. So how do we approach this mathematically? Well, how do we know when the diffusion current has stopped? Well, we will take a slightly different look, which will help us mathematically. Now remember that we have created an electric field in this region. We have positive charge here, negative charge here. If you bring a positive unit charge to this environment, we see that it wants to go from left to right. So the electric field is pointed from left to right. Okay. Now, because we have an electric field, we can say that we have a diffusion, we have a drift current. Remember that associated with an electric field, we have a drift current. So equivalently, what we can say is that this junction will stop carrying these diffusion currents when the drift currents associated with the electric field cancel the diffusion currents associated with this difference in densities. So that's the key concept that helps us quantify things here. All right, so I'm going to write these conditions so that we know what we are facing. So we say, for example, diffusion current of electrons must be equal to a drift current of electrons okay. This is for equilibrium, meaning that eventually things have stopped. No more current is flowing. So equivalently, what we can say is that actually there are currents flowing, but they're canceling each other. There's a drift current flowing this way, there's a diffusion current flowing this way, and they cancel each other. Okay, and a similar condition should hold for holes. So we say diffusion current of holes must be equal to drift current of holes. And these two are what we call equilibrium condition. So let me change the color to something else. So we say equilibrium condition is satisfied when these two hold. Okay, so now it seems that we are a step closer to writing an equation to describe the equilibrium condition. We will look at the second equation. Diffusion current of holes must be equal to the drift current of holes. The drift current of holes. So let's equate these two. So diffusion current of holes, that's d sub p dp over dx times q is equal to drift current of holes. So mu p e times q. What happened to the negative sign that I had here? That negative sign is gone because I'm trying to cancel two currents that are flowing in this junction. So that's why we don't have a negative sign here. All right. Okay, so we have an equation in terms of E, the electric field inside here, the density of holes, and the gradient of hole densities, and then some other constants. Okay, well, how do I handle this equation? Well, why don't we try to integrate both sides with respect to x and see what happens? So I will have to divide by p and then cross out this q with this q. So what I have is dp over p is equal to mu p e dx. So far so good? Okay. So what do we do with this equation? Well, let's integrate. We will integrate both sides. So we integrate dp over p is equal to mu p integral of e dx. We integrated both sides. Now, we are integrating from a certain limit to a certain limit, so we have to look at our integration limits. I will perform this integration from here to here. So this is the x dimension. I will call this x1 and this one x2. x1 is this edge of the depletion region inside the n-type material, and x2 is this edge of the depletion region inside the p-type material. So because this integration is with respect to x, I am integrating from x1 to x2. So far so good. How about this side? Well, this side we are integrating with respect to p, the hole density. The hole density at x1, is given by p sub n, and that is equal to ni squared over nd. So this would be p sub n, and the hole density at x2, is given by p sub p. So that's p sub p. So that is the integration that we have to perform. Okay. Now, the integration on the left is not that hard. We just have dp over p, so that's log of p. We can satisfy the limits. That's good. The integration on the right is a little tricky. Is the electric field constant so that we can take it out of the integral? No, we don't know. We don't know what the electric field looks like. In fact, it's not that hard to prove that it's not constant. So the electric field is not constant from x1 to x2, which means we cannot take it out. But maybe we don't even have to take it out. Maybe what we can say is go back to physics and remember what we mean by integral of electric field with respect to distance. What is that? That is the definition of voltage, if you remember. So to find the voltage difference between x1 and x2, we need to integrate the electric field along x from x1 to x2. Except that there's a negative sign involved. So we just have to be careful of that. Otherwise we're good. So why don't we do it this way then? We will integrate this side, so that becomes dp log of p sub p over p sub n is equal to mu p. And then this integral represents v of x1 minus v of x2. Okay, not v of x2 minus v of x1, because remember, there's a negative sign relating voltage and integral of electric field. So I will write it here if you want to remember. So v from a to b is equal to minus integral from a to b of electric field dx. Okay, so I can write that as v of x1 minus v of x2. Okay, and we might call this v0 for simplicity. So this whole thing, we call it v0. And now we will go ahead and replace p sub p and p sub n with with na and ni squared over nd. So I can write v0 is equal to dp over mu p. So that mu p goes under, this mu p goes under that dp. And then we have log of p sub p, that's na, divided by this, ni squared over n sub d. Ni squared over n sub d. So that is the voltage. This voltage is from here to here. The voltage measured between these 2 points is given by this expression. Okay, that's very interesting. Now, remember something about this fraction? If you remember Einstein's relation, it told us that the d over mu is equal to kt over q. So d over mu is equal to kt over q. That means that I can write v0 as kt over q log of na and d over ni squared. This voltage is called the built-in potential or built-in voltage. It's built in because we didn't do anything to the device. As soon as we formed the crystal from P and N, this voltage was developed inside, simply because the carriers could not stay where they were. The electrons flowed from one side to the other. The holes flowed from one side to the other, and we created an electric field. We created a voltage between those two. So if I ask you, for that voltage, V0, where is the positive side, where is the negative side, how do you decide? Well, you can see here that we have positive charge here, negative charge here. The electric field is oriented this way. So the voltage would have its positive side on this over here and its negative side over here. And that makes sense because you can see that all of these are positive here. So V0 came out to be positive, and V0 was defined as V of x1 minus a V of x2. And the result is positive, and it all agrees with our intuition. Okay, so KT over Q, if you remember, is about 26 millivolts. This is what we call the thermal voltage, 26 millivolts at room temperature. So that's something to remember. And then the other values depend on the structure that we have. Na and Nd are the doping levels that we have chosen for these two sides. So we have higher doping levels, V0 is higher, and vice versa. Ni squared is a given value, 10 to the 10, at the room temperature. So that's not under our control. All right, so the built-in potential is what's developed inside the junction. Now, at this point, I would like to give you a quiz to think about it a little. So here's the quiz. Is there an electric field outside the depletion region? So we have seen an electric field inside here, but how about here? Is there an electric field? So give it some thought. I'll give you 90 seconds. All right. Did you figure out whether we have an electric field or not? Well, the answer is that no. At least in the first order, there is no electric field out here. And to prove that, we can go back to our physics principles and remember Gauss's law that told us the amount of electric field that we can measure on a surface is proportional to the charge, the net charge enclosed by that surface. So Gauss says that if you take a surface and you find the total net charge in here, then the electric field on the surface that we measure is proportional to that charge. So it's very easy to show that the electric field has to be 0 here and here. So let's change the color of the pen. Actually, I need a different color. Let's see if I can go to orange. Okay, so I will take a Gaussian surface like so. I will put one edge here and another edge over here. So what is the net charge in the surface? It's 0 because we have as many positive ions as negative ions. So the net charge inside the surface is 0, which means the integral of electric field has to be 0, and the electric field turns out to be 0 on this surface and on this surface. And we can move this surface up and down here, or this surface up and down here, and we will see that the electric field is always 0. So the electric field only exists inside the depletion region, not outside. Of course, we are making an approximation here, meaning that suddenly at this point everything stops, and suddenly at this point everything stops. It's not exactly like that. There's a gradual transition here, but for our purposes, that approximation is reasonable. Okay, so the electric field only exists inside the depletion region, not here, not here. That means that there is no voltage drop here and no voltage drop here, because voltage and electric field are related. If the electric field is 0 everywhere, then the voltage from A to B also has to be 0. So these are good things to remember. So we say electric field is 0, which means voltage drop is also 0 in the what we call neutral regions. These are neutral regions because they don't have any net charge in them. They have charge neutrality. Okay, very good. So we have come this far and we have learned all of these. So the significance of the built-in potential is that when the junction reaches that potential, the diffusion currents will stop. So initially, when we form this junction, we have lots of electrons here, not many here, and there's not really any depletion region. But the electrons begin to flow this way, the holes begin to flow this way, the depletion region becomes wider and wider, the voltage difference becomes larger and larger, and at some point, the electric field is large enough to stop these currents, and at that point, we have this much voltage difference between the two. So as you can see, we surreptitiously avoided finding the electric field itself. We have not found the electric field. We don't know how it varies from here to here. That's not that difficult. We can do it, and we can easily see it in different books. But for our purposes as circuit designers, we were really interested in the built-in potential that appears across the device and not much about what the electric field looks like inside the depletion region. Very well. We are now ready to make a few observations about the equilibrium condition before wrapping this up and going into the reverse bias condition. So let me write the observations here. Okay, first observation. You might be wondering that I wrote these equations from this condition for holes. Diffusion current of holes must cancel the drift current of holes. I never wrote the equation for the electrons. What happens if I repeat this analysis for the electron currents? So by equating this one, mu n n e q, to this one, dn over dx q. Well, you can carry out the calculations, and it turns out that you get exactly the same result. So same V0 expression is obtained if the electron currents are considered. Okay, so in other words, the built-in potential created when we make this calculation versus when we make this calculation are consistent. They do not disagree with each other. Everything is good. Okay, next observation. So let's change to a different color. Next observation is the following. Let's pick some typical values for these doping densities to see what kind of value we obtain for the built-in potential. So if Na and Nd are on the order of 10 to the 16 per cubic centimeter. So They are not necessarily 10 to the 16. They could be anywhere between 10 to the 15, maybe up to 10 to the 18th. But just roughly speaking, if they are about 10 to the 16, then if you plug them in here, and remember that ni squared is 10 to the 20th, because it's 10 to the 10 to the power of 2, then we see that V0 is approximately equal to 26 millivolts times log of 10 to the power of 32 divided by 10 to the power of 20, and that comes out to be about 720 millivolts. 720 millivolts. So we say that in a typical case, the amount of built-in potential that a PN junction holds is around 700 to 800 millivolts. So we say typical values of V0 are from 700 to 800 millivolts. Okay, just as a rough number to keep in mind. Very well. The next observation is as follows. V0 is localized. And by that, I mean the V0 that we have calculated exists only from here to here. We do not have any other voltage in these areas, in these regions. And we saw the reason for that just now, right? Because we said the electric field was 0, the voltages were 0, so the only voltage that we have is localized to this edge of the depletion region and this edge of the depletion region. If we measure the voltage difference between these two, we get that amount. If we go any farther, we don't have any voltage contribution by this section and that section. Okay, and last observation is that we cannot measure V0 from outside. Strange but true. But by this we mean if we take this junction after it has reached equilibrium and connect a voltmeter between these two terminals, we do not see anything. We see 0. Why? Why is it that this voltage of 700 to 800 millivolts does not reach our voltmeter when it's connected to the two terminals? So there's a very interesting reason for that. All right, so remember that we have the PN junction formed as a single crystal. It's a crystal. Now, to be able to measure anything at these 2 points, we have to connect these pieces of wire to the PN junction. As soon as this wire touches this PN junction, we form another junction here and another junction here. Now, these are not PN junctions because we are connecting a metal to a semiconductor. So it's a different type of junction, but it does have a built-in voltage, just like this junction. So now, if I change the color of my pen, you can see that we have another built-in potential here and another built-in potential here. So if we use Kirchhoff's voltage law, as we start from here and go here, we have 1 voltage, nothing here, 1 more voltage, nothing here, 1 more voltage. And when we add up these 3 voltages, we get 0. Interestingly, this voltage and this voltage add up to the negative of this voltage, and they cancel each other. So that's one explanation as to why the built-in potential cannot be measured from outside. Okay, this completes our study of the p-n junction in equilibrium. It's not a particularly exciting concept because we don't really use a p-n junction in equilibrium, but it's the simplest case. So with all these equations and these insights that we have developed, we are now ready, we are better prepared to go into more interesting and useful cases. For example, the reverse bias case. All right, so let me add a page here. Okay, so now we will study the p-n junction in reverse bias. And this time we actually apply something from outside to the junction. We don't leave it alone. Now, the definition of reverse bias is as follows. We take our p-n junction, let's say with the n side on the left and the p side on the right. You can draw it however you want, but here's one possibility, n here and p here. All right, we have the two terminals on the two sides, and we connect a battery between these two. The battery has to be connected in a very specific way for us to have reverse bias. Reverse bias means the positive end of the battery goes to the n side, and the negative end of the battery, negative terminal of the battery, goes to the p side. So you can see why we call it reverse bias, because we're trying to apply positive to the n side and negative to the p side. Okay, they oppose each other, so to speak. All right, so this is called reverse bias. If we confuse these two, if we apply negative here and positive here, then that will not be reverse bias. So we have to be careful about this polarity and this type of material that we have here. Okay, so what exactly happens when we apply this voltage? Let's call it VR, reverse bias voltage. All right, so we applied, let's say, 1 volt in reverse bias to the p-n junction, and we would like to see what happens. Okay, well, let me draw the depletion region that we had in the equilibrium condition first. So, in the equilibrium condition, we had some positive ions here and some negative ions here. Okay, because we had to have an electric field to stop the diffusion of the currents, the diffusion of the carriers. Okay? But now that we apply a voltage, we are doing something else that affects the behavior of the junction. So this positive is connected here, and it wants to push away positive charge, or it wants to attract negative charge. So this positive terminal wants to attract negative charge. Where does it get that negative charge? It takes it from the electrons that we have here. We have lots of electrons. So upon connecting this battery to this device, some electrons go from here to the battery, right? So we take some electrons away, which means the depletion region becomes wider, because we took more electrons away than what we had in the equilibrium condition. Similarly, on the p side, some holes depart and go to the battery, so the depletion region on the hole side also becomes wider. So when we reverse bias the junction, because of the influence of this battery, we end up taking some mobile charge out of the n side, some mobile charge out of the p side, and we make the depletion region wider. That's all that happens, really. Nothing else, nothing significant happens in this case. So again, After we do this, after the depletion region becomes wider, we don't have much current flowing. The device doesn't seem that exciting, just like the equilibrium condition. But it's actually quite useful. Okay, all right, so that's all we saw. We say that in reverse bias, the depletion region becomes wider. Okay, so that's not bad. But what good is this device anyway? I have a device, and all that happens is that when I apply 0 voltage to it, it has a certain depletion region. When I apply a reverse voltage, let's say 1 volt, depletion region is wider. Is that any good? Well, such a device can act as something very interesting and very useful. So let me take a step back and refresh your memory about capacitors from basic physics. So remember that the capacitor can be constructed as 2 parallel plates. And what we remember from basic physics is that if we take these 2 plates and move them apart from each other, move them away from each other, so if we go like so, then the capacitance between these 2 terminals decreases. So if the first one has a capacitance of C1 and second one has a capacitance of C2, C1 must be less than C2. That's something we remember from basic physics. Okay? All right. Now, this principle applies to this junction. So let's see if we have a capacitor to begin with. Yes, we do. Why do we have a capacitor? Well, remember this region has no voltage on it, no voltage drop on it, no electric field, and it's a reasonable conductor. It's not as good as a piece of metal, but it is pretty good because we have doped it very heavily. So I can consider all of this as one plate of a capacitor. Similarly, on this side, I can consider all of this as one plate of a capacitor. So indeed, we have a capacitor. In a regular capacitor, you would fill this with some sort of dielectric, some sort of insulator. Here we have some sort of insulator, maybe not an excellent insulator, but it is because it doesn't have any mobile charge in it. There's no possibility for charge to go from here to here anymore, right? So we can see that this device forms a capacitor. One plate here, some sort of insulator in between. All right, now, when we go from diffusion to, when we go from equilibrium to reverse bias, we can examine this junction and the capacitance associated with it. So, in equilibrium, this is what we have. We have a narrow depletion region. So our capacitor looks like this. That's the equivalent capacitor. So one plate here, insulator in between. Now when we go to reverse bias, let's say 1 volt across the junction, then what happens is that the depletion region is wider. So the device now looks like this with some exaggeration. And that means that the capacitor now looks like this. So we see that the capacitance of the junction, the capacitance that you could measure between these 2 terminals, changes as we go from equilibrium to reverse bias. The capacitance decreases because equivalently the 2 conductive plates move away from each other. Equivalently, this region of insulation expands in width. So that's a very interesting effect. Okay, so we have a capacitor whose value can be controlled. Here it has a higher value, here it has a lower value. And it can be controlled not mechanically, we don't have a knob to turn, but electronically by a voltage. If we apply a voltage across it, the larger the voltage in reverse bias, the wider depletion region, the smaller the capacitance. So this is what we would call an electronically variable capacitor. So electronically variable capacitor. And in fact, we have a name for this device because this device is very useful in practice. And this device is called a varactor. Varactor is a capacitor whose value can be controlled by a voltage. Now, can I plot the value of this capacitor as a function of this voltage? Yes. So here's what it looks like. So this is what we will call Cj. Cj denotes junction capacitance. It's a PN junction. It just happens to have a capacitance, so we call it Cj. The horizontal axis is the voltage. Now, it's customary to draw the capacitance for a negative voltage. Here comes the little bit of a confusion because VR with this type of polarity is actually positive, okay? So you have to be careful. We will write here, I will just write here reverse bias. And as long as we are in reverse bias and the voltage in reverse bias increases, this is what we get. As long as the absolute value of the reverse bias increases. Okay, so this is what we get. And in fact, there's an expression for this capacitance. It goes like this. Cj is equal to something in the numerator, which is called Cj0. Cj0. Cj0 is the value of the capacitance when the voltage across the junction is 0, right here. So this value is Cj0. Now we would like a declining function, and that function looks like this. 1 minus VR over V0. All right, so I'm going to write VR here at the risk of creating confusion. So this plot says VR has to be negative to be in reverse bias. This equation also says VR has to be negative, because if VR is negative, then this would be like plus absolute value of VR. As the absolute value of VR increases, this term increases, and the capacitance drops. So this equation is consistent with this plot, and in this equation VR has to be negative, so that's fine. This equation and this plot are not quite consistent with this drawing here, but don't worry about it. So long as you know what reverse bias means, we should be okay. So this is the equation for the junction capacitance of a simple diode in the ideal case. And it says that as we change the voltage across the capacitor, the capacitance value changes. All right, now is that any good? What do we do with such a device? Well, yes, remember the Bluetooth transmitter? Remember that in the Bluetooth transmitter we had an oscillator. So let me refresh your memory about that transmitter with this my collection, which I called my Circuitpedia. All right, so we said that the transmitter consists of an oscillator with a control input. And when the control jumps between 0 and 1, 0 and 1, let's say 0 volt, 1 volt, 0 volt, 1 volt, the output frequency jumps up and down. 2.4 gigahertz plus a small amount, 2.4 gigahertz minus small amount. It just is a small perturbation around 2.4 gigahertz. Okay, now this oscillator needs a mechanism to change its frequency. And this voltage, this control voltage, causes that frequency change. So something inside this oscillator must be sensitive to voltage, so that when the voltage goes from 0 to 1, it changes the value of that device inside the oscillator, and when that changes, the frequency of oscillation changes. And that's where a varactor comes into the picture. So in order to build an oscillator for Bluetooth or for many other applications, this is what we would do. So let me just draw that here. I have some room. So oscillator for Bluetooth. Okay, so what we are looking for is, here's the oscillator. And inside this oscillator, we will use a PN junction in reverse bias. It goes into the internal nodes of the circuit. We don't know exactly how. There's something in there. But this PN junction can be controlled from outside. So when we give it zeros and ones, so let's say 0 volt, 1 volt, or 0 volt, half a volt, the capacitance of this PN junction, this varactor, changes. And when the capacitance changes, the frequency of oscillation changes. So we have a high frequency, and then low frequency, and then high frequency, and then low frequency. So that's a simple and beautiful example of how a reverse biased PN junction can become beneficial in circuit design. And we see that this equation tells us how that would happen. All right, now you might be confused a little, saying a PN junction has 2 terminals, a capacitor has 2 terminals, but does this guy have 2 terminals? It has a terminal here, and it seems that it has a control terminal. Well, no, it doesn't need to have 3 terminals, and in more advanced courses you will see how such an oscillator can be designed. But the point is that what goes in here is a varactor, and one possible way of implementing a varactor is a PN junction. So that's what a reverse biased junction can do. Very well. We are approaching the end of our time. Let me see if there's anything else that I need to mention here. Okay, I think I mentioned this. V0 is the built-in potential that we just calculated. So depending on the doping levels, we have a certain V0 that goes in here, and that will give us the equation for the junction capacitance. All right, in this lecture, we studied the PN junction in equilibrium and in reverse bias. In the next lecture, we will go to the PN junction in forward bias. And it suddenly becomes much more interesting and gives us other possibilities for using this device in circuit design. And that allows us to come up with lots of examples of circuit applications of diodes. I will see you next time.